Okay, welcome students. Now today we'll be discussing regarding simple harmonic motion or oscillations and waves. The first part of the topic will be starting with oscillations. Now in this very chapter we'll be essentially dealing with the simple harmonic motion. But before coming to the simple harmonic motion, we should be familiar with certain definitions regarding which will be later used while dealing with the simple harmonic motion. Now the first thing which we'll be focusing on, we'll try to distinguish between what is the difference between the periodic motion and oscillatory motion. So oscillatory motion and periodic motion, we'll essentially try to find out the distinction between the periodic motion and oscillatory motion. Even before coming to the oscillatory motion, if we will try to define periodic motion, we define it as a motion which repeats after regular intervals of time. So a motion which repeats after regular intervals of time, is known as a periodic motion. So any motion which repeats itself after regular intervals of time is known as periodic motion. So the necessary and sufficient condition for a motion to be called as periodic motion is only one thing, and that is it should repeat itself after regular intervals of time. Now to understand this periodic motion, we can have certain examples of this periodic motion. You have to understand any motion which repeats after regular intervals of time may be designated as a periodic motion. Now let's take the example of rotation of Earth. Now if we talk about a rotation of Earth, now see, Earth, there are two types of motion which Earth is involved with. One is rotation of Earth around its own axis, and second is a revolution of Earth around Sun. So second is a revolution of Earth around Sun. So Earth is essentially involved with two types of motions. The one, rotation of Earth around its own axis, and second, revolution of Earth around Sun. Now, the rotation of Earth around its own axis every time takes equal intervals of time, and that's approximately equal to 27.3 days. And which you also call as 1 month, normally 1 month. So every time Earth takes 27.3 days to complete one rotation about its own axis. So what we can mention here, or what we can conclude here, is that rotation of Earth around its own axis is a periodic motion. Now on the similar context, if we take the example of revolution of Earth, now all the planets, as we know, they revolve around Sun in an elliptical orbit according to Kepler's laws. But every time Earth takes equal time to complete its revolution around Earth, and that is what we call 1 year, or approximately 365 days. So revolution of Earth around Sun is also a periodic motion. So the only condition for a motion to be called as periodic motion is it should repeat after equal intervals of time, because every time Earth takes approximately 365 days to complete its revolution around Sun. On a similar context, we can have various other examples, like we can have hands of a clock. Hands of a clock. Now suppose, for the sake of argument, if we take the hour hand, it takes all the time 12 hours to repeat its position. Suppose the hour hand is currently at position 1. After 12 hours, it will again be at the same position. After 12 hours, it will be again at the same position. So we can say that the hands of a clock, suppose the hour hand, the motion of hour hand of a clock is a periodic motion, and the time after which the motion repeats itself is known as time period. Obviously we'll come to that in the later part of the lecture while we define time period. Similarly, you can have minute hand. All the time it will take repeat its motion after regular intervals of time. The second hand, or every time it will take equal amount of time to repeat its motion. So all those motions which repeat itself after regular intervals of time are known as periodic motion. So before trying to compare or distinguish between the periodic motion and the oscillatory motion, the only necessary and sufficient condition for a motion to be called as periodic motion is that it should repeat after equal intervals of time. Now, if we try to focus on the oscillatory motion, any motion of a particle which is to and fro motion, or you can say back and forth motion. A particle, once the motion is in the form of a to and fro motion or back or forth motion, and if the motion repeats after equal intervals of time, the to and fro motion plus regular intervals of time, plus regular intervals of time. See, as far as the periodic motion was concerned, only one condition for the motion to be called a periodic, that the repetition of the motion should be after equal intervals of time. But in contrary to that, as far as the oscillatory motion is concerned, in oscillatory motion we say it's a to and fro motion, or back and forth motion, and the motion should repeat after equal intervals of time. Then you call that motion as oscillatory motion. So we're discussing the oscillatory motion, and why we stated that any motion which repeats or which is in the form of a to and fro motion or back and forth motion and repeats after equal intervals of time, we can call that motion as oscillatory motion. Now let's have some examples of the oscillatory motion. Let's have the sibling mass system. Now let's have another example before we try to explain this. Let's have it a YouTube. Okay, let's focus on these two examples. Now if we have a sibling mass system, while we have a sibling, a vertical undergoing vertical oscillations, and we have a mass m attached to it. Now what we do is, if we stretch this mass downwards and then release it, the motion of the sibling or the motion of this mass will be in the form of this. And if we neglect any damping considerations, the motion essentially in this case will be known as oscillatory motion, because if you assume any arbitrary origin like this mass will be doing the motion like this. It will be going up, it will be going down, then again up and then again down. So this type of motion is known as oscillatory motion. So condition, it is a to and fro motion and the motion is repeating after equal intervals of time. We call this as the oscillatory motion. Now this is a sibling mass system. Sibling mass system. Now, on similar context, if we consider a liquid in a U-shaped tube, Now, what we do is, under normal conditions, the liquid height on both the columns would be identical. But what we do is, if you push the liquid on one side of the tube and then let it freely undergo oscillations, what will happen is, once we push this liquid downwards, the liquid on this side will go up, and then while reaching it at a certain height, the liquid on this side will stop, and now this liquid, because of more weight of the body, it will come down, and the liquid in this side will go up. So this continuous. On one side, the liquid column on this side goes up, then it comes down, then it goes up, and then it comes down. This will also come under the domain of oscillatory motion. So before moving further, what we can conclude here is that as far as the periodic motion is concerned, any motion which repeats after equal intervals of time is periodic motion. But as far as oscillatory motion is concerned, for oscillatory motion, there are two conditions. One, it should be a to and fro motion, about a fixed point, and second, the motion should also repeat after equal intervals of time, which essentially means whatever conditions the motion under periodic consideration should have, those conditions should be filled in oscillatory motion as well. And that is regular intervals of time, repetition of regular intervals of time. But apart from that condition, in oscillatory motion, it should be a twined flow motion. Now here, what we can conclude here is that, like every oscillatory motion, is periodic, but not vice versa. Means every oscillatory motion is periodic, but every periodic motion is not oscillatory. Now let's take an example. In the earlier context, while giving the examples of periodic motion, we took the example, suppose a revolution of Earth. Now revolution of Earth around Sun is periodic because it is repeating after equal intervals of time, but it is not oscillatory. Because under oscillatory, a motion, it cannot go under a complete circular motion and a complete revolution. Oscillatory should be this way. It is about a fixed point, it's going on one extreme, coming back, going to another extreme and coming back. That's oscillatory. So every periodic motion is not oscillatory. But every oscillatory motion is periodic. Suppose we took the example of spring mass system. It is oscillatory motion, but automatically it is periodic because the motion is repeating after equal intervals of time. Suppose we took the example of a liquid in a U-shaped tube. It is oscillatory, but automatically it becomes periodic. So every oscillatory motion is already periodic, because in periodic, the conditions which the motion should have to be periodic, those are already filled in the oscillatory motion. Because in oscillatory motion, apart from being a twined flow motion, it should also repeat after equal intervals of time. So once the oscillatory motion repeats itself after regular intervals of time, it automatically becomes periodic as well. So that is what we mean by this sentence, that every oscillatory motion is periodic but not vice versa. So we took the example of, we have a spring mass system. It is oscillatory, but automatically it is periodic because the motion is repeating after equal intervals of time. Similarly, the liquid in a U-shaped tube. But on the other context, we are talking about, suppose, the revolution of Earth around Sun. It is periodic, but not oscillatory. Similarly, we may talk about the motion of a minute hand of a clock, motion of an hour hand of a clock. Those are periodic, but those are not oscillatory. So this is the distinction between the periodic and oscillatory motion. Now there is again one fine distinction we call as oscillation and vibration. What is the distinction between oscillation and vibration? Essentially, there is a, normally these oscillation and vibration, these are the terms oftenly used as synonyms of each other. But if we go deeper, there is some fine distinction between oscillation and vibration. But for understanding the difference between oscillation and vibration, and before we actually come to the topic where we have to discuss the simple harmonic motion, we should understand two terms known as time period and frequency. Once a motion is oscillatory, we have to distinction between, we have to understand the terms like time period and frequency. Because once we understand time period and frequency, we can understand the basic difference between the oscillation and vibration. As I mentioned earlier, these oscillation and vibration, they are often used as synonyms of each other. Now time period, suppose we are talking about the spring mass system. I am taking this point as the reference. And now, once I have stretched this mass and raised it, now this mass is undergoing the oscillatory motion. So that once the mass goes up here and it starts to come down, now the position where from this mass again starts to come down is known as extreme position. So, and it comes down and goes to other extreme. So once this spring mass system from here, one extreme to another extreme, and comes back to its original position, the total time taken by a body to complete one oscillation is known as time period. The total time taken by a body to complete one oscillation is known as time period, and it is designated by capital T. Suppose once we discuss it regarding unperiodic motion, we talk about motion of Earth around Sun. So once we stated that every time Sun takes 365 days or 1 year to complete its revolution around Sun, so we can say time period of revolution of Sun is 365 days. We talked about rotation of Earth around its own axis. So we know rotation of Earth around its own axis takes around 27.3 days. So we can say time period of rotation of Earth around its own axis is 27.3 days. We talked about, suppose, the motion of, suppose, our hand of a clock. Because our hand of a clock, we can say every time it takes 12 hours to repeat its motion. We can say time period of our hand of clock is 12 hours. So time period we define as the time taken by a body to complete one oscillation. It is denoted by T. Its SI unit will be obviously second. It's simply time. Its SI unit is second. Another term we define as frequency, and this frequency is denoted by nu. It's a Greek symbol. We pronounce it like nu. Now frequency, mathematically we write frequency as it is inverse of the time period. Now what do we mean physically by the frequency? Frequency we define as number of oscillations completed per second. So the number of oscillations carried by a periodic motion in 1 second is defined as frequency, and it is SI unit. Obviously it is second inverse, it is 1 by second. It will be like this, 1 by second, or you can write it second inverse, or that second inverse we call as hertz. So the time period has a SI unit of second, and frequency, which mathematically we define as inverse of the time period, its SI unit is 1 by second, second inverse, or hertz. Now why we define these two terms at this juncture is we want to have that fine distinction between oscillation and vibration. As I earlier mentioned, that these oscillations and vibration are normally used as synonyms of each other, but the fine difference is that in case of an oscillatory motion, if the frequency of oscillation is low, so if frequency of an oscillation is small, if frequency is small, you call it as oscillation. And if frequency is large, we call it as vibration. We call it as vibration. Suppose if a particle is oscillating this way, it's moving slowly, we can call it oscillation. But if the motion is this way, it's fast, its frequency is more, we can call this motion as vibration. So essentially, technically, oscillation and vibration are both synonymous of each other. The requirement for both types of motion is same, that is the repetition of regular intervals of time and the to and fro motion about a fixed point in case of both oscillation and vibration. But the difference is, in case the frequency of the motion is small, like a body is moving like this way, you may call it as oscillation. But once the frequency is more, a body is moving this way, you call it as vibration. So this is the essential distinction between oscillation and vibration before we come to the next point. Okay, so we were defining the time period and frequency while we try to distinguish between the oscillatory and vibratory motion. Now, let's take a simple numerical based on this, how we calculate time period and frequency. Suppose we have an issue like this. Now let's take the simplest example of a human heart. So a human heart, in normal cases, let's say it has 80 vibrations per second, or 80 beats to be more precise is 80 beats per second. So a human heart beats 80 times per second, and what you are supposed to do is you are supposed to calculate its time period and frequency. Calculate its time period and frequency. This is the simplest case before we move further. So a human heart beats 80 times per second. We have to calculate the time period and frequency. Obviously we know the time for 80 vibrations or 80 periods, 80 beats is equal to it's not in 80 beats per second, it's 80 beats per minute. So time period for 80 beats is around 1 minute, means 60 seconds. So what will be there? Because once we have to discuss the frequency, we have to see how much beats are there in 1 second. So time for 1 beat, time for 80 beats, it is 60 seconds. So for 1 beat, or the time taken for 1 beat, it will be obviously it is less than 1 second. So time taken for 1 beat is 60 divided by 80. Because time taken for 80 beats is 60 seconds, time taken for 1 beat, it will be 60 divided by 80. This will be approximately 0.75 second. So the time taken by a human heart to complete 1 beat is 0.1 second, and this is essentially which you call as time period. So the time period of a human heartbeat is 0.1 second in case we consider it to be 80 beats per minute. Now, as far as the frequency is defined, we define frequency mathematically as it is inverse of time period. T we calculated here to be 0.175 seconds. It is 1 divided by 0.75 seconds. So 1 divided by 0.75 will be approximately 1.33. Since we have taken the SI unit of time period to be the SI unit of time, and that's second, so the frequency will also come in the SI unit, that is hertz. So the frequency is 1.33 hertz and the time period is 0.75 seconds. So this is essentially how we will calculate, obviously in the complex situations also the essence of the physical significance remains same of the time period and frequency, and we try to distinguish that in case this frequency is small, we may call it oscillatory motion. In case this frequency is large, we may call it as vibratory motion. Okay, we will define the periodic motion. Why we define periodic motion as a motion which repeats after equal intervals of time. Now, what we will try to do is, before coming to the simple harmonic motion and defining simple harmonic motion, we need to essentially understand the concept of periodic function. Now, on a similar context, why we stated that periodic motion is a motion which repeats after equal intervals of time. On similar context, we say a function which repeats its value after regular intervals. A function which repeats its values after regular intervals is known as a periodic function. So a function which repeats its values after regular intervals is known as a periodic function. Now let's take examples to deliberate on the issue and try to understand what a periodic function is. Now mathematically, in trigonometry, we see sine and cosine function or trigonometric functions. Sine and cosine function or periodic functions. Once we say sine and cosine function or periodic functions, But suppose if we talk about tan, this is not periodic. Tan is not a periodic function, but sine and cosine functions are periodic functions. Now let's try to discuss that. Now, if we have the values of, let's take theta. Let's write it right here, sine of theta, and let's write here cosine of theta. Suppose if we know if theta is 0, we know sine 0 is 0 and cos 0 is 1. Now let's then take, if we take say 45, we know here sine of 45 is 1 upon root 2, cos of 45 is also 1 upon root 2. Then if we take say sine, then we take 90, sine of 90 is 1, cos of 90 is 0. Then again obviously then we will be taking say 180, sine of 180 is again 0, cos of 180 is minus 1. Then obviously we will be taking this 360, sine of 360 may again come to be 0, this may again come to be 1. Now once we try to analyze these values of theta and their corresponding values for sine theta and cos theta, what we see here is that the values of sine theta and cosine theta, they repeat after regular intervals. Regular intervals in the context regular intervals in the context the regular intervals in the context that once whatever value was, once theta was 0, sine theta is 0, the same value will be repeated after 360 degrees. So once after 360 degrees, the value of sine theta again comes out to be 0. Similarly, once the value of theta was 0, the value of cosine of theta was 1. After 360 degrees, again the same thing happens, that cosine of 360 degree will again be equal to 1. And once we try to plot these things graphically, see, let's start. Here we have theta, and you can have it here. If this axis we can have say sine of theta, and this axis we have theta, the graph we may get it this way. And if we try to plot the graph for cosine of theta with theta, the graph we may get this way, which essentially means once theta is 0, sine theta is also 0. Once theta is, say, let's call this complete cycle, because here what you see is after this much of interval, the motion again repeats itself, and this much of interval is known as time period. And here it is equal to 2 pi or 360 degrees. 2 pi or 360 degrees. So in case of cosine theta, once the theta is equal to 0, cosine of theta is equal to 1. And once the theta comes out to be 90, the cosine of theta comes out to be 0. So this whole we call as, from here up to here, we call it as a time period, because this is the time after which the motion repeats itself. And if you take this, this will be 1/4 of a time period, means this is t/4. This is half of the time period, you may write it t/2. And this you may write maybe 3t/4. And this will be final t. Or in terms of angle, if you write it in by, its total is 2 pi, so this much here you will be pi/2. Here this will be equal to pi, and here this may be equal to, this one will be equal to 2 pi, and this will be equal to 4, this will be equal to 3 pi/2. Or in terms of degrees, you may write it 90 degree, you may write it 180 degree, we may write it 270 degree, and we may write it 360 degree. So sine and cosine functions, since they repeat after equal intervals of time, those functions are known as periodic function. But the same thing is not happening in case of tan. If you analyze the same analogy in case of the tangent of theta, you will see it will go from 0 to infinity. So it doesn't repeat its values after equal intervals of time. So those functions which repeat their values after regular intervals of time may be called as periodic functions. And how do we mathematically now represent these periodic functions? Now here on one axis we have sine of theta, and on the other axis we had theta. Now let's try to analyze here. If we have any function, so let's represent this function as f of t. We can write this function as, let's suppose this is sine of omega t. We can write it this one, this sinusoidal function. Or if you have another function, let's represent that function as g of t. You may write it, this is equal to cosine of omega t, because you can represent a periodic function by either a sine function or a cosine function. Now this omega here, we know this omega is equal to 2 pi upon t, where capital T is the time period, omega is the angular frequency. So using it here, we will have it sine of 2 pi by t into the small t. Similarly, this is cos of 2 pi upon t into this small t. Why this capital T is the time period, omega is the angular frequency. So this is essentially how we define a periodic function. But taking it one step ahead, we can define in general any function, a periodic function. We may define it like this. We may define it like this: a1, suppose sine of 2 pi by t into small t, plus b1 cos of 2 pi by t into small t. But here we will not define this a1 and b1, we simply call these a1 and b1 their coefficients, or they might coefficients. We'll later name these coefficients because they are known as Fourier coefficients. So a linear combination of, just try to understand here, this is a periodic function having time period t. This is another periodic function which is represented by a cosine function again having time period t. The linear combination of these two, is also a periodic function. So a linear combination of two periodic functions having same time period. Just imagine here, time period here is same. So a linear combination of two periodic functions having same time period, here we have represented by capital T, is also a periodic function. And then there is one more thing. In case, suppose for a particular these functions, sine and cosine functions, we know the time period after which the function repeats itself is 2 pi or 360 degrees. It essentially means whatever value you will have for say sine of theta, let's call it whatever value you will have for sine of theta, you will have same value for sine of theta plus 2 pi. Whatever value you will have for cos of theta, you will have same value for cos of theta plus 2 pi. Because after 2 pi time period, the function will repeat its values, which means whatever value will be there for suppose sine of 0, will have same value for sine of 0 plus 360 degrees. Whatever value we will have for suppose cos of 10 degree, we will have the same value for cos of 10 plus 360 degrees. So So this is essentially how we define a periodic function. Means a function which repeats its values after equal intervals is known as periodic function. So, and here we try to define that a linear combination of this periodic functions having the same time period will also be a periodic function. Now let's have once again the mathematical analysis of this periodic function. So if function is periodic, in that case whatever will be f of t plus capital T. Just remember, capital T is the time period of periodic motion and small t is any time interval. This should be equal to f of t. Just suppose in case of sine and cosine functions, so it will be f of sine or cosine, it will be f of say t plus 2 pi. This will be equal to f of t because 2 pi is the time period or the period of the function. Similarly, we will have f of t plus this here the time period t is equal to 2 pi. Similarly, we will have f of t plus twice this time period. This will again be equal to f of t, which means we will have f of t plus 2 into 2 pi means 4 pi. This will again be equal to f of t. This is how we mathematically define a periodic function. In general, we can say it will be f of t plus n times 2 pi, which means 2 pi n. This will be equal to f of t, where the n can be 1, 2, 3, 4. So this is essentially how we will define a periodic function. So in case of sine and cosine functions, in general, we can write if f of t we will represent as sine of 2 pi n small t upon capital T. Capital T is the time period, so it can be 2 pi times t. When n is 1, if n is 2, it will be 4 pi times t. N is 3, it will be 6 pi times t divided by t. Similarly, in case of cosine function, you can write it is cos of 2 pi n t upon capital T. Now just imagine here that the period in both of these periodic functions, that is time period, is same. It's capital T and it's capital T. Now the linear combination of these two, let's in general represent it as y of some function. If we can write it, it's like this: a1 sine of 2 pi n t upon capital T plus, let's give some other constant here, b1 cos of 2 pi n t upon capital T. So in general, if you start giving values to this n as 1, 2, 3, 4, so in general you will have y like this. Y of t, it may be equal to some a0 plus, if we have a1, let's give this value n equal to 1 sine of 2 pi, n is 1 t by capital T, then giving value of n as 2, we can write it an and bn. Giving this n as 2, we'll have it a2 sine of 2 pi into 2, that's 4 pi into t divided by capital T, and it will continue. Then start giving values to this b, it will be b1 cos of 2 pi t by capital T plus b2 cos of 4 pi t upon capital T, and it will continue. While these coefficients a0, a1, a2, b1, b2, they are known as Fourier coefficients. as Fourier coefficients. So this is how we mathematically try to analyze a periodic function. So before moving on, what we stated here is that a motion which repeats after equal intervals of time is known as periodic motion, and on a similar context, a function which repeats its value after equal intervals of time is known as the periodic function. As an example, we took the sine and cosine function that as periodic functions, because we know both sine and cosine functions repeat their values after regular intervals of time. That interval of time is known as time period, and in case of sine or cosine functions, that is 2 pi in terms of radians or 360 in terms of degrees. Now we define periodic functions because we'll be able to understand what are periodic functions once we know what are not periodic functions. For the sake of argument, as a rule, we say the logarithmic or exponential functions are not periodic. Logarithmic or exponential functions are not periodic. Logarithmic or exponential functions are not periodic functions because the logarithmic or exponential functions doesn't repeat their values after equal intervals. Now let's graphically try to understand some of the functions which are not periodic, because we should have some contrast between periodic and non-periodic functions. Now let's say we have a function like this. In another case, we may have a function like this. Let's say here we have e raised to the power of omega t, and here we have t, and obviously it is an exponential function. It will be this way. As another example of this non-periodic function, if we write here, suppose this axis is e raised to the power of minus omega square t, and this we write as t, this may be this way. Now see, this function is not periodic because there is not the periodic function. So let's suppose this is not logarithmic or this exponential function, but in this thing you will see, if we have suppose one cycle, this is a separate time period, another cycle this will have a different time period, this will have a different time period if we extend here. So a function or a motion which comprises of more, but the motion is comprising of more than one time period, or which may not be periodic. So this is not a periodic function, because this function cannot be represented by a single harmonic function or a single periodic function. You cannot represent it by any single periodic function. Similarly, if we have this case, if we have here e raised to the power of omega t and this axis is t, now what will happen if suppose t tends to be infinity? What will be e raised to the power of omega t? E raised to the power of omega t will be equal to e raised to the power of infinity. Omega is t is infinity, e raised to the power of infinity is equal to infinity. So what you see here is that once t approaches infinity, this function on the y-axis also approaches infinity, means its values will not repeat after equal intervals of time. So this function is also not periodic. Now let's take this example. Now here what will happen if suppose t approaches infinity? So you will have here 1 by e raised to the power of omega square t. So it will be 1 by e raised to the power of infinity, that is 0. So it essentially means once t approaches 0, the function on the y-axis, which is this here, e raised to the power of minus omega square t, also it approaches 0, which essentially means whether this function or this function, they are not periodic functions because they cannot be represented by a single periodic function in this case, and in the rest of the two cases we saw that their value doesn't repeat after equal intervals of time. In this case it approaches up to infinity, and in this case it goes down to 0 and doesn't repeat itself, and these functions are known as non-periodic functions. Now, we say here, as far as oscillatory motion is concerned, once again coming back to the basic definition, that a motion which repeats itself of equal intervals of time is periodic, and a periodic motion which is in the form of to and fro motion or back and forth motion is known as oscillatory motion. Oscillatory motion. And we say the simplest form of oscillatory motion, the simplest form of oscillatory motion is known as simple harmonic motion. This is known as simple harmonic motion, or SHM. And this is the topic about which most of the coming lectures will be revolving around, that is simple harmonic motion. It's the simplest form of harmonic motion, or is the simplest form of the oscillatory motion. Now we'll have the further analysis of the definition of this simple harmonic motion, maybe based upon the Hooke's law, but just try to understand that simple harmonic motion, as of now we may say it's the simplest form of oscillatory motion. Means simple harmonic motion will also be a periodic motion, means simple harmonic motion may also need to be represented in terms of a periodic function. But before that, now let's have some periodic function or some type of oscillation. Let's represent it by a sine curve. Let's suppose this is theta, and say this is some physical quantity, let's call it y. Now we can see here the motion starts from here, it completes half the oscillation here, and full cycle of the motion is completed here. If suppose this axis we define as suppose the displacement. Now this position, this is known as the mean position. So here the particle is at the mean position, and the displacement of particle above mean position in this axis is known as displacement. So here the particle is displaced from the mean position, here the particle is this much displaced from the mean position. Once the particle reaches there, its displacement from mean position is this much, and once the particle is here, its displacement from the mean position is this thing. And once the particle moves further, its displacement from the mean position goes this way. So what we can see here, once the particle reaches at this particular position, the displacement of particle is maximum. Displacement of particle from mean position is maximum at this point, and this point is known as amplitude. So amplitude of particle undergoing simple harmonic motion, or in any oscillatory motion for that sake, is the maximum displacement of particle from mean position. So this displacement will be A. Let's suppose we represent it by capital A. Similarly, if we move to the negative half cycle, or the motion of a particle in other direction, so if we have a simple pendulum which is oscillating, this is the mean position. Once the particle going this way, we can take it to positive. Once it going this way, we can take it as the negative cycle. So here again, the same thing is happening. If you see here, the disposition of the particle, or this displacement of particle from the mean position is known as amplitude, and the position from which the particle retraces its path. Suppose we have a simple pendulum, a simple pendulum is going to this extreme and then it comes back, and the position from which the simple pendulum comes back is known as extremum or extreme position. So here what we have to try to do is, we have to try to understand the concept of amplitude, because this is how we will define the equation for simple harmonic motion. So we stated here that amplitude is the maximum displacement of particle from mean position. Now let's say this way, suppose we have here a simple pendulum, and we have given some displacement to the simple pendulum. The simple pendulum is going to this axis, and from here on it comes back and going to this end. So here, if we call as y, here y will be equal to 0 because this is the mean position of the particle. So at mean position of the particle, the displacement of particle from the mean position obviously will be equal to 0. Then once the particle moves here, y increases, and at this position, the displacement of a particle becomes maximum, and that is known as amplitude. Similarly, on this side, displacement of a particle again becomes maximum, but in a different direction. You can say it is minus a, because displacement being vector, if you take one side of a displacement, means the displacement on one side of the origin as positive, on the opposite side we have to take negative, so we can have it minus a. Now we're continuing with the simple harmonic motion, and what we'll in the current lecture, what we'll try to do is we'll try to study the characteristics of simple harmonic motion, and we'll try to define simple harmonic motion. By the end of the day, once you are familiar with the characteristics a simple harmonic motion executes, so this will incorporate how we define displacement in case of a simple harmonic motion, what do we mean by the velocity of a particle executing simple harmonic motion, and in addition to that we'll be dealing with acceleration of a particle in simple harmonic motion. We have to discuss phase, what we will understand by phase of a particle in simple harmonic motion. So to understand this, what we'll do is from this diagram, what we'll try to understand is we'll try to understand the simple harmonic motion, the displacement of a particle in simple harmonic motion, taking into consideration a uniform circular motion of a particle. Now suppose the particle is at a position P and this is making an angle, suppose theta, where we can say theta is equal to omega t for the sake of argument. Now once the particle is executing a uniform circular motion, the particle moves from here, it goes to here, it goes to here, it goes to here. Let us suppose this coordinate, this is x, and let's call this as y. So once a particle moves along in a uniform circular motion, its x coordinate as well as y coordinate will definitely change. Now the change in x coordinates, the change along x coordinate may be represented by somewhat like, suppose x is equal to a, if the vertical coordinate, it will be a cos of omega t, and y coordinate will be equal to a sine of omega t, or a cos of theta, or y will be equal to a sine of theta. This is simply what we're doing here. We're trying to do the resolution of a vector. This component will be with which makes angle theta, it will be the x component or the cos component, and this one will be the sine component. Now if we try to draw the projection on the diameter of this particle on simple harmonic motion. Now in case we're interested in at a particular position point P, we'll say the projection of a particle executing simple harmonic motion on diameter of a particle will represent simple harmonic motion. So here we will make a statement that in case of a particle executing uniform circular motion, the simple harmonic motion will be represented or given by projection of a particle along any diameter of a particle in circular motion. Now first thing, before going to define the phase of a particle, or before going to derive the expressions for displacement, velocity and acceleration of a particle, what we can do is we can define here phase of a particle executing simple harmonic motion. Now just try to understand that as far as phase of a particle executing simple harmonic motion is concerned, now this phase, this is a physical quantity. This phase is a physical quantity which gives us the position and configuration of a particle executing simple harmonic motion at any instant of time. Now let us, for the sake of argument, let's make the same representation in this way. So suppose we are interested in here, the particle was initially here, let's call it Q, and from Q, particle has moved to position P. Initially, when suppose time is equal to 0, the particle is at a position Q, and when time is equal to suppose T, particle is at a position P. So it has moved in this direction, and it has covered an angle of suppose theta, where say theta is equal to omega t. Now this theta or omega t is known as phase of a particle. The reason being, suppose if we know initially the particle is here, if we know suppose the phase of a particle is, for the sake of argument, if in terms of degrees, if we say suppose the phase of a particle is 45 degrees, so means particle has moved from here up to here traversing an angle of 45 degrees. So by knowing the phase of a particle, we can determine the position of a particle at any instant of time. So phase is a physical quantity which gives us position of a particle in simple harmonic motion at any time. So this theta is known as phase. Suppose if you say phase of a particle is say 90 degree, how would you determine the position of a particle executing simple harmonic motion? By knowing its phase. If you know initially the particle is here, suppose if the phase is 60 degree, you would say after covering an angle of 60 degree, the particle will now be here. So by knowing phase of a particle, we can be sure of knowing how to calculate the position of a particle at a later instant. Now here the question is, in atoms, in case the particle starts from origin, there can be two different things we can discuss here. One, if the particle starts from origin, this is one option. And second thing is, if the particle doesn't start from origin. So if the particle doesn't start from origin, if the particle doesn't start from origin, means in some cases when t is equal to 0, the phase of a particle is also equal to 0. In that case, you may write the displacement of a simple harmonic motion, suppose like a sine of omega t. Because here you will see, if say t is equal to 0, obviously sine of omega t will be equal to 0, and y will also be equal to 0. This is one condition. That in case the particle starts from origin, t is equal to 0, sine of omega t will be equal to 0 because sine 0 is 0, and y will be equal to 0. This is one condition. But the second case here is, in case the particle doesn't start from origin. In case the particle doesn't start from origin, it means when t is equal to 0, y will not be equal to 0. Once the process has started, particle has already covered some displacement, like in this case. Means suppose if we consider this as mean position, once the time starts, when t is equal to 0, particle has already covered some displacement. Let's call suppose this angle as phi 0. Now this phi 0 here, this phi 0 is the phase of the particle when the process has started, and this phi 0 is known as initial phase, or you also call it as epoch. This is known as initial phase or epoch. So in case you have to write the equation, displacement equation for this type of a simple harmonic motion, you may write it like this: y is equal to a sine of, let's suppose, omega t plus phi 0. So phi 0 is the initial phase. Now here you can be sure that even if t is equal to 0, this term may become 0, but obviously y will not be equal to 0 now, because there will be some non-zero term left in this equation, because this will be sine of omega t plus sine of phi 0. This term may become 0, but sine of phi 0 will be non-zero, and hence displacement will be non-zero. So from this discussion, what we concluded here is that one, the the simple harmonic motion may be represented as the projection of a particle of executing in uniform circular motion along any diameter of it, like this. While x component you may write as the cosine one and the y component as sine one. Both are periodic functions, and the combination of these two periodic functions will also be a periodic function. That's one. Second, once we try to discuss the phase of a particle, we mentioned that phase is a physical quantity which gives us the position of a particle executing simple harmonic motion at any future time. If we know the phase of a particle currently, we can calculate phase of a particle at some future time. Then there were two different things, like there can be cases where a particle executing simple harmonic motion starts from origin, means when time is equal to 0, the displacement is equal to 0. Under those circumstances, the displacement equation we may write this way. And there can be situations where when you have started analyzing the process, means when t is equal to 0, particle has already covered some displacement, means there is initially some phase there even when time has started. So here means when you have started the process from here q, particle has already covered this much of angle. So in those circumstances, even when t is equal to 0, the displacement of particle will not be equal to 0. This angle or this much of phase which the particle initially has when you have started analyzing the process is known as epoch or initial phase of the particle. Under those circumstances, we can have the displacement equation for a particle executing simple harmonic motion as a sine of omega t plus phi 0, because whenever this t is equal to 0, y will not be equal to 0 under these circumstances. Okay. Continuing with the simple characteristics of a particle executing simple harmonic motion is, we will take the simplistic case of the particle executing simple harmonic motion of a simple pendulum. So we know a simple pendulum where we have a heavy mass attached to essentially a massless string with a rigid support. This is a simple harmonic. This is a simple pendulum, and what we will next try to do is we will just give a displacement to the simple pendulum and then let it free to oscillate. What will happen is this simple pendulum, this pendulum or this bob will move to this side. It will stop there, come back to this original position, and then move to the next extreme. So its motion will be essentially this way. On one side, it will move to this extreme, and then it will come back to its original position, and then because of inertia of motion, it will move to the next opposite direction here. Now this position of the pendulum or any particle for that sake, this is known as mean position. So at mean position, displacement of a particle is 0. This is known as mean position. Mean position. So mean position is the original position of a particle where the particle was staying at rest when where there is no restoring force acting on the particle. And this position, this is known as extremum or extreme position. Extremum, or this is also known as turning point, because this is a position where from the pendulum or the bob now turns back, and this is known as turning point. And same applies to this. This is also known as extremum or turning point. Extremum or turning point. Okay. Now, taking this into consideration, we'll try to discuss the displacement, velocity, and acceleration of a particle, and we will try to find out the relation between these physical quantities. If we first discuss here, the first one, if we talk about the displacement of particle. Displacement. This displacement, let's represent this displacement as y. Now, displacement, we know, displacement is a physical quantity which essentially will give us the effective distance traveled by a particle in simple harmonic motion. Displacement means once the particle, because wherever we have to define displacement of a particle, we have to have some origin, and that origin here is known as mean position. Means we'll be calculating displacement of a particle with respect to this position. So this position means at this position or at origin, what we can call it, the displacement of a particle is 0. This position is known as mean position. Now, since displacement being a vector, the displacement on one side of this mean position in this side will take y as positive, because displacement being a vector, and other side of this mean position will take displacement of a particle as negative. Now, looking at here, looking at this position, now once a particle comes from here, suppose at this position y is equal to 0, particle moves here, y increases, y increases, y increases, and once particle reaches here, y becomes displacement of a particle from mean position becomes maximum, because the particle doesn't move beyond it, because from this position particle comes back, so displacement again starts decreasing. And this position where the displacement of a particle becomes maximum, so here displacement of a particle will become maximum, and that maximum displacement of a particle is known as amplitude. So maximum displacement of a particle is known as amplitude. So here the displacement of a particle from mean position is 0, because this is itself a mean position, and here the particle is at a maximum displacement from mean position, because from here onwards the particle turns back. That's why it is known as a turning point or extremum. So at this position displacement of a particle becomes maximum, and that maximum displacement of a particle is known as amplitude. So we can say here y max is equal to A, or you can say plus A. Now moving to this side, again once a particle reaches to the origin, because of inertia of motion the particle moves to the other extreme, and finally while reaching here the particle stops momentarily here and returns back to its original position. This is also known as extreme or turning point, and here again the displacement of a particle is maximum. But displacement being a vector, we have to designate, if we have designated displacement on right to origin as positive, we have to write it, turn this part of the displacement as negative. So here we will write as y is equal to say minus A. So magnitude of minus A plus A will be same, because the amplitude will be maximum, it will be constant, but for the sake of direction this will be equal to plus A and this will be equal to minus A. Now here, so displacement, first let's discuss displacement only. So displacement of a particle, you write it like this: y is equal to A sine of omega t. Or even if the function is cosine, you can write y is equal to A cos of omega t. And in both the circumstances, now you know what can be the sine of omega t. What can be just maximum value? Its maximum value can be equal to 1, which once this is equal to 1, y will be equal to A. So y maximum will be equal to A. Similarly, what can be the maximum value of cos of omega t? That can again be equal to 1. This can again be equal to 1. So y max in both the cases comes out to be equal to A. That is what we were discussing here, that maximum displacement of a particle is known as amplitude. That can be also mathematically represented by these equations, because these are those both periodic functions. You can write a displacement for a particle executing simple harmonic motion by a periodic function sine of omega t or cos of omega t. It depends upon whether the function is sinusoidal or cosine. Means if the particle starts from mean position, you will write it sinusoidal. If the particle starts from extreme position, you will write it cosine function. Like here, you can write it this way. Suppose the motion can be this way, or the motion can be this way. If the motion, suppose this is theta, say, or this is any physical quantity y, this is y and this is theta. So if the motion is this way, it starts from origin, you will write sine of omega t, and if the motion starts from the extreme position, you write it cosine of omega t. In terms of simple pendulum, if you try to when to start write with the sine of omega t, when cos of omega t, suppose if you have start the motion of a particle from here, so it starts from the mean position, it will be a sinusoidal curve. If it starts from extreme position and you let it go, then the motion will continue, and that will be the cosine of omega t. But in both of these cases, this omega t here represents phase, and same here omega t represented phase. In both of these cases, what you have assumed is initial phase is 0, or epoch of the this function is 0. But in case there also exists some initial phase of a particle, then you may write the displacement equations as y is equal to a sine of omega t plus or minus, it depends on whether the initial phase, whether the particle leads the origin or it lags the origin, plus minus phi 0, or y is equal to a cos of omega t plus minus phi 0. So both these equations can be represented for displacement of a particle executing simple harmonic motion. Okay, now before, because we'll start with the displacement and we'll try to proceed with the velocity and then to acceleration and then try to graphically correlate these two. Now, if we define here, what are the conditions, essential conditions required? What are the essential conditions required for a particle? What are the essential conditions required for a particle to execute simple harmonic motion? To execute simple harmonic motion. We'll come to the another type of definition where we define the simple harmonic motion on the basis of Hooke's law, that the displacement of a particle in simple harmonic motion will be defining this simple harmonic motion on the basis of Hooke's law, where the restoring force is directly proportional to the displacement of the particle from its mean position and should be directed opposite to it. We'll come to that. But before that, if we have a particle here, if we have taken the example of simple pendulum, what are the essential conditions which a particle should execute or which a particle should possess in order to execute simple harmonic motion? And there essentially are two conditions. There essentially are two conditions for a particle to execute simple harmonic motion. One is known as inertia, and second is known as elasticity. Means for any particle to execute simple harmonic motion, the two necessary and sufficient properties which a system should possess is inertia and elasticity. Inertia, obviously we know inertia measures mass of the body, and elasticity you may relate it with restoring force. Now let's try to analyze same thing on the basis of this simple pendulum. See, what we say is, once we have displaced the simple pendulum from the mean position and it has reached to this extreme. Now the first thing is, what brings this simple pendulum back to its mean position? What brings this simple pendulum, or what brings this bob back to its mean position? That is restoring force. Because restoring force will try to bring this bob back to its mean position. So unless and until the body doesn't have a restoring force, it will not come back to its mean position. So restoring force is essential for bringing a body back to its mean position. But suppose the restoring force brought this pendulum back to its mean position, and in case the body stops at mean position, again there will be no simple harmonic motion. But the body doesn't stop at mean position. Once it reaches mean position, restoring force becomes 0. But the bob doesn't stop here. Bob moves to the next extreme. So what made bob to move from mean position to extreme position? That is because of inertia of motion. So both restoring force and inertia are responsible or required for a particle to execute simple harmonic motion. Restoring force brings the body back to its mean position, and inertia makes the body to move from mean position to extreme position. So this continuous jungle between these restoring force and inertia are responsible for a particle to execute simple harmonic motion. Okay, continuing with the characteristics of a simple harmonic motion, if we now discuss the velocity of a particle executing simple harmonic motion. Velocity will present here as V. Now, in case the displacement of a particle, now let's for some time, let's suppose that the initial phase of a particle is 0. Let's represent displacement of a particle as y is equal to a sine of omega t. Let's call this as equation 1. Let's be familiar with the terms. Y is displacement of a particle, a is maximum displacement or amplitude of a particle, omega into t, in totality it is the phase of a particle, because this is the argument of trigonometric function, sine is a trigonometric function, so omega t is the argument of trigonometric function, or we may call here is the phase of the particle. Omega is the angular frequency and t is any orbital time. Now, if we differentiate, we know differentiating displacement with respect to time gives us velocity of the body. So if we differentiate this displacement with respect to time, this is what we will call as velocity of the body. So this will be d by dt of y. So y is this thing, that is a sine of omega t. Now, there is a basic rule while processing for the differentiation, that if you have any constant involved within a function which has to undergo differentiation, the constant comes out of the differentiation. So this a will come out. A is amplitude which is constant. So this will be equal to d by dt of sine of omega t. Now differentiation of, we know d by, suppose, let's say this way, d by d theta of sine theta. We know differentiation of sine theta is cos theta. Okay, now we'll have velocity is equal to a is here, but this is sine of omega t. So omega will come out, and this will be equal to, its differentiation will be omega times cos of omega t. Because here the internal differentiation of omega t will be equal to omega, and that omega will come out. That is omega times cos of omega t. So we'll see what we get here is velocity of a particle comes out to be equal to omega a cos of omega t. Let's give this equation a number as equation 2. So this is the expression we get for velocity of a particle executing simple harmonic motion. But just take into consideration that we have taken the displacement of a particle as a sine of omega t. If we take here as y is equal to a cos of omega t, then accordingly things may change. But as far as if we take the sinusoidal function as the displacement of a particle, the velocity of a particle comes out to be equal to omega a cos of omega t. Okay, now let's try to present this equation. This is the expression for velocity of a particle in simple harmonic motion. Now let's try to analyze this equation and try to put it in different forms like the one. So we have a basic trigonometric identity, sine square theta plus cos square theta is 1. In place of theta we have omega t. So sine square omega t plus cos square omega t, this is equal to 1. Now what I intend to do is, I intend to substitute this cos of omega t in terms of sine. So what I can do is, this sine square may go this side, we'll write it this way. Cos square omega t is equal to 1 minus sine square omega t. Or this square may go this side, this will become root, so you will have cos of omega t, this is equal to under root of 1 minus sine square omega t, because this square will form a root on this side. Let's call this as equation 3. So in equation 2 we have cos of omega t. We will use the value of cos of omega t from equation 3 in equation 2. So using using equation 3 in equation 2. So what we'll get is V is equal to omega A, and here in terms of this thing, cos of omega t, I may write under root of 1 minus sine square omega t. Now if this A, if I take this A within the root, so within the root in terms of A, I have to write A square because the square and the root later will cancel. So this A, I can multiply both this A with 1, it will be A square, and similarly I have to multiply A square with this term. So if I take A within the root, I will write it this way: V is equal to omega under root of this A into 1. This will be equal to A square because I am taking A within the root. The square root once again comes, cancels, and A will come out. Minus A square sine square omega t. Fine. Okay, now already from equation 1, see from equation 1 what we know is, from equation 1 what we know is y is equal to A sine of omega t. So here we have A sine of omega t, A square sine square omega t. So this will be equal, this term will be now equal to y square. So I can write it V is equal to omega into under root of, this is A square minus this A square sine square omega t. A sine of omega t is y, so A square sine square omega t will be equal to y square. So this comes out to be V is equal to omega under root of A square minus y square. Once again, if we discuss the terms here, omega is the angular frequency of a particle, A is amplitude, and y is the displacement. Let's call this equation as equation 4. If I further try to analyze this velocity of a particle executing simple harmonic motion, now suppose let's take some special cases here. Now in case we talk about the mean position, if we talk about the mean position, at mean position the displacement of a particle is 0. So we have to see what will be velocity of a particle at mean position. Once this displacement of a particle is 0, so putting it equation 4, using it in equation 4, you will get V is equal to omega into under root of A square minus 0, because y is equal to 0 minus 0. So square and root cancels, V will be equal to omega A, and this will be the maximum velocity of a particle. So from here what we conclude is that velocity of a particle will be maximum at mean position. Now let's take the second case. If we talk about the extreme position, at extreme position we know displacement of a particle is equal to amplitude. So once you use y is equal to A in equation 4, so using in equation 4, what we'll get is V is equal to omega under root of A square minus y is now equal to A, so this will again be equal to A square. A square minus A square is 0, so velocity will be equal to 0. Now these are some essential conclusions which we are getting from the velocity of a particle executing simple harmonic motion, that once the particle crosses the mean position, velocity of a particle is maximum and it is numerically equal to omega A, and once the particle is at the extreme position, velocity of a particle is 0. And it has to be 0 because at the extreme position, particle has to momentarily stop and then it will come back. So at extreme position, velocity of a particle is 0, and at mean position, velocity of a particle is maximum. So continuing with the velocity of a particle in simple harmonic motion, we derive this expression v is equal to omega under root of a square minus y square. This expression we derived, probably this was an equation 2 or so. What we can do is, we can square this equation on both sides. So squaring on both sides. So what we'll do is, it will be v square is equal to omega square into a square minus y square. Now this omega square, we can bring it down to v square, we'll get it v square divided by omega square is equal to a square minus y square. This minus y square will come on this side, this will become plus y square, so this will be v square divided by omega square plus y square is equal to a square. I got this minus y square on this side, this became plus y square. Now if we bring this a square to the denominator, this will be divided to this term as well as the second term. So what we'll get is v square divided by omega square a square plus y square by a square is equal to 1. Now, this is an essential equation which we have obtained for a particle executing simple harmonic motion. V square by omega square a square plus y square by a square is equal to 1. The terms are v is velocity of a particle, y is displacement of a particle, omega is the angular frequency, and a is the amplitude of a particle. And we know this is an equation of ellipse. This is an equation of ellipse. So it means the velocity of a particle executing in simple harmonic motion gives us the equation of an ellipse. And if we will try to graphically show this equation, if we have, say, if this axis is the velocity and this axis is the displacement, the graph between velocity and displacement will be an ellipse, so it will be somewhat like this. Whereas this term, this side, this will be equal to omega a, maximum value of velocity, and this will be equal to a because maximum value of displacement is amplitude and maximum value of velocity is omega a. So if we ask a question that what is the relation, graphical relation between the velocity and displacement of a particle executing simple harmonic motion, so it's an ellipse, and which has come from this very equation. Now, so as a general case, the graph between velocity and displacement of a particle executing simple harmonic motion is an ellipse. But there can be a special case. There can be a special case. Suppose if omega is equal to 1, if angular frequency of particle is 1 in any SI units. So once you use omega is equal to 1 in this case, once you try to substitute this omega is equal to 1 in this case, what we get is v square divided by a square plus y square by a square. This is equal to 1. Now, or you can take a square common, get it to this side, you will get v square plus y square is equal to a square. Now, this is an equation of circle. So now the graph between the velocity and displacement of a particle in case of simple harmonic motion comes out to be a circle. But we just have to take it into consideration that this comes out to be a circle under a special case once we have assumed omega to be equal to 1. But as a general rule, the graph between velocity and displacement of a particle executing simple harmonic motion is an ellipse and represented by this very equation. And if we put the omega is equal to 1, then the graph between velocity and displacement of a particle executing simple harmonic motion comes out to be equal to, circle. Now the third parameter or the characteristic of a particle in simple harmonic motion is very important, and on the basis of what we will be defining in fact the simple harmonic motion, that is acceleration of a particle. Now acceleration, we know the equation for velocity of a particle in simple harmonic motion we reached here. V is equal to omega A cos of omega t. Let's call this now as equation 1. We know this omega t is the phase of a particle, omega is angular frequency, A is amplitude, and V is velocity of a particle in simple harmonic motion. Now if we differentiate equation 1, if we differentiate equation 1 with respect to time, what we'll get is, obviously we know differentiating velocity with respect to time gives us acceleration. So let us represent acceleration with small a, because we have represented amplitude by capital A. The small a is the amplitude. So write it, this is dv by dt. So this is d by dt of v is velocity. So using the value of velocity here, we'll write it is omega a cos of omega t. Now omega and a will take out of differentiation. We will have a is equal to omega a will take out of differentiation, both being constants. You have d by dt of cos of omega t. Now we know differentiation of cos of theta is minus sine of theta, but because of internal differentiation this omega will come out. So we will have differentiation of cos of omega t. Obviously this will be equal to minus sine of omega t, but because of internal differentiation of this part, omega will come out. So this will be omega times sine of omega t. Let's call this as equation 2, and let's call this part as equation 3. So once we using equation 3 in equation 2, what we'll get is we'll have a is equal to, we'll have a minus sign here, we'll have already, which is this omega a, and terms obtained after differentiating this function is this thing. This is omega sine of omega t. Okay, now this omega into omega becomes omega square. You have a is equal to minus omega square a sine of omega t. So this is the expression we get for acceleration of a particle executing simple harmonic motion. Now also we know that displacement of a particle we have represented as y is equal to a sine of omega t. So if we use this a sine of omega t, in place of this we can write it y. So we have a is equal to minus omega square y. This is one of the interesting expressions which we get for the acceleration of a particle executing simple harmonic motion. Now since omega being constant, we can have acceleration is directly proportional to displacement, but there will be a minus sign. Now on the basis of this expression we can define simple harmonic motion of a particle. In the earlier part of the lecture we defined that simple harmonic motion is the simplest form of oscillatory motion, but now we can have more technical statement for the simple harmonic motion. We may define that simple harmonic motion is that type of motion where the acceleration of a particle is directly proportional to displacement but is directed in opposite direction. We may again repeat this statement for the simple harmonic motion, that in case of simple harmonic motion the acceleration of a particle is directly proportional to displacement but is directed opposite to it. This minus sign means it is directed opposite to it. So this essentially gives us the definition of simple harmonic motion. This gives us the definition of simple harmonic motion. Okay, now if we discuss some cases that what about mean position? At mean position, we know displacement of a particle is 0. So once we put y is equal to 0, in this expression we get acceleration is also equal to 0. Which means acceleration of a particle at mean position is 0. Now let's take the other extreme, which we also call as extreme position. Extreme position. At extreme position we know y is equal to a. So once we put y is equal to a in this equation, we will get acceleration is equal to minus omega square a, and this will be the maximum value of acceleration. So again, we can say that the acceleration of a particle at mean position is 0 and acceleration of a particle at extreme position is maximum. Okay, we got expression for acceleration like this: a is proportional to minus y, which means the graph between acceleration and y is linear. It will be a straight line. The way we try to find out the graph between velocity and displacement of a particle in simple harmonic motion, which was found out to be ellipse, and say on the same footing the graph between acceleration and displacement of a particle executing simple harmonic motion is a straight line. So this will be the graph what we will be getting this in case of acceleration of a particle in simple harmonic motion. It will be a straight line, but obviously there is a negative sign. That's why once you can see here in this quadrant acceleration is positive but displacement is negative, and here displacement is positive but acceleration is negative. One among the two has to be negative because of this thing. Otherwise, suppose had it been this way, acceleration is proportional to y, to be a simple straight line. So the graph should have been between first and third quadrant, but owing to this negative sign, the graph is between second and fourth quadrant. Okay, now we have discussed, we have got the expression for, let me write it here. We got expression for displacement, y is equal to a sine of omega t. For the velocity we got v is equal to omega a cos of omega t, and for acceleration we got va is equal to minus omega square y, or y is a sine of omega t. Now based on these three equations what we derived for a particle in simple harmonic motion, that's one for displacement, second for velocity, and third for acceleration, we'll try to have some comparative analysis of these particles. Okay. Now if we talk about here, the first thing, if we write here the physical quantity, so if we talk about here, first the displacement, for displacement the equation we have is y is equal to a sine of omega t. Okay. Then if we talk about here, second, say we have velocity, and third we have acceleration. Now, in case of displacement, the equation is y is equal to a sine of omega t. In case of velocity, we have b is equal to omega a cos of omega t. And in case of acceleration, we have a is equal to minus omega square a sine of omega t. Now, the second thing, if we talk about mean position, y is equal to 0, which means mean position. So at mean position, obviously displacement is equal to 0, but once it is mean position, we found out velocity is maximum, which we got at V maximum is equal to omega A, and acceleration at mean position is also 0, because these are the things which we derived while deriving those expressions. Now if we talk about extreme position where y is equal to A, we know displacement at extreme position is y is equal to A, velocity at extreme position is equal to 0. Extreme position is equal to 0, and acceleration at extreme position, this is equal to minus omega square A. It's also maximum. Okay. Now if we talk about the graph, if suppose for a sinusoidal function, the graph for displacement versus, say, let's talk about time, we'll have a graph like this, but this is a sinusoidal function. For velocity, it will be a cosine one. So if we try to plot the graph between velocity and time, we'll have somewhat this cosine function, because you can see it from here. And if we talk about acceleration, the graph for acceleration, obviously it will be same as that of displacement, but with negative sign, means you will have it this way. So displacement, velocity and acceleration, the corresponding equations are given here. Their values at mean position and the extreme position are given. At mean position, obviously displacement is 0, velocity is maximum, acceleration is 0, and at extreme position, displacement is maximum, velocity is 0, and acceleration is also maximum. Their corresponding values are given. And as far as the graphs are concerned, the displacement versus time graph is given. The velocity versus time graph will be a cosine one. The acceleration versus time graph will be also a sinusoidal one, but opposite to that of the displacement owing to this negative sign. So the coordinates, the cycles will get inverted. We'll have the negative cycle where the positive cycle of displacement used to be, and positive cycle of acceleration where negative cycle of the acceleration, a negative half cycle of the acceleration used to be. Okay, so what we are doing is we are trying to compare displacement, velocity and the acceleration of particle. If we try to find out the phase relation between the displacement, velocity and acceleration of a particle, what we will try to do is we will try to write them in the same plate form, like this is in the form of a sine. What I will try to do is I will try to write the equation for velocity also in terms of sine, and similarly I will try to play with the equation of acceleration as well. So in case equation for displacement is y is equal to a sine of omega t, I can write v is equal to omega a. I can write it like this: sine of omega t plus pi by 2, because we have a famous trigonometric identity that cos of theta is equal to sine of theta plus 90 degree, or pi by 2. Means whatever value cosine will have a particular angle, sine will have the same value at 90 degree plus that angle. Suppose means cos 10 degree will be same as sine of 10 plus 90 degree. So that way it goes. Okay, so this is the expression for velocity we get. And similarly for acceleration thing, what I can do is I can write acceleration is equal to omega square a sine of omega t plus pi. Because what I have done is I have wrote here like in terms of minus sine of omega t is equal to sine of omega t plus pi. Because after a change of 180 degree, the sine inverses its value. Means whatever value of sine 90 is, Sin 90 plus 180 will be exactly that value but with negative sign. So this trigonometric identity we have used there. So we have got now acceleration for particle executing simple harmonic motion given by this equation, velocity given by this equation, and displacement given by this equation. Now we can have some essential conclusions from here that, see, if we compare equation for displacement and velocity of a particle, we can see there that the velocity of a particle leads the displacement by a phase angle of pi by 2. Because here you see sine of omega t, here it is sine of omega t plus pi by 2. So what we can see here is velocity leads displacement by pi by 2. And similarly, now if you compare equation for acceleration and equation for displacement, you see here it is sine of omega t, it is sine of omega t plus pi, which essentially means that acceleration of a particle leads the displacement by a phase angle of pi. So acceleration leads displacement by a phase angle of pi. And obviously, if you compare acceleration and velocity, acceleration leads velocity by a phase angle of pi by 2. Acceleration leads velocity by a phase angle of pi by 2. So this is the phase relation between displacement, velocity and acceleration, where we have tried to put the equations for displacement, velocity and acceleration on a similar platform, and we compare the corresponding equations between displacement and velocity, between displacement and acceleration, and between velocity and acceleration, and we reached to the conclusion that velocity leads displacement by pi by 2, acceleration leads displacement by pi, and acceleration leads velocity by pi by 2.